My dear students, in the previous video, we have discussed about the properties of a binary operation, namely closure property, commutative property, associative property, the existence of identity, and the existence of inverse property. And now, in that identity property, I am going to give additive identity now. Additive identity. Additive identity. Additive identity means it depends upon the operation, addition operation. Additive identity is 0. 0 is the additive identity. Because the additive identity 0 leads to operates between two elements. If any element in a set, given set, if you operate with additive identity, it gives us that element only. For example, A belongs to an element in the set S. If 0 is the additive identity, 0 is the additive identity, for A plus 0 equal to 0 plus A equal to A itself. So this is the nature of additive identity. The additive identity 0, if you add with any element in a set, it gives the element itself. For example, in a set Z plus, it's an algebraic structure. In this structure, addition operation operated upon the elements of the set of integers. For example, 8 plus 0 equal to 0 plus 8 equal to 8 itself. If you operate with a negative number also, minus 15 plus 0 equal to 0 plus minus 15 equal to minus 15, like that. So additive operator is 0, additive identity is 0, it operates upon any element in a given set, gives the element itself. This is the nature of additive identity. Next, multiplicative identity. The additive identity is, it defines on the set is that a real number set or rational number set, everything except the natural number set. Additive identity is not in a set of natural numbers, because natural number set start from 1 only, 1 to infinity. You know the natural number set n. N is a set of natural numbers. It is from 1 to etc. up to infinity. Therefore, 0 is not in the element of the set n. Therefore, there is no additive identity in the set of natural numbers. So, except the set of natural numbers, in all other sets, the additive identity is that. Now, multiplicative identity. Multiplicative identity is 1. Multiplicative identity is 1. If you multiply, the binary operation is multiplication here. If you multiply any element in a given set, it gives the element itself. Because A is an element in the set S, it implies A into 1 equal to 1 into A equal to A. This is the nature of the multiplicative identity. 1 is a multiplicative identity, and 1 exists in all the sets N, Z, Q, R, and the set of complex numbers also. 1 plus I0 in the set of complex numbers, 1 plus I0 is a multiplicative identity. Imaginary part is 0, real part is 1. See, for example, in a set of 3 by 4 is a rational number Q, and 1 is in Q. Therefore, 3 by 4 into 1 equal to 1 into 3 by 4 equal to 3 by 4. This is the, here, the element in the rational set multiplying with the multiplicative identity, we will get the element itself. So this is the nature of multiplicative identity. Then we will see additive inverse now. Now I am going to define additive inverse. So far we have seen additive identity which is 0. We have seen so far additive identity which is 0 and multiplicative identity which is 1. Now additive inverse. Additive inverse. An element in a set, its inverse, its additive inverse is minus a. Then only the element and its additive inverse equal to the additive identity. This is the definition of additive inverse. If A is an element in set, yes, minus A is a corresponding additive inverse of the element A. For each and every element, there is a corresponding inverse element according to the additive identity, additive addition operation, I mean. So A plus minus A equal to minus A plus A equal to additive identity 0. Therefore, minus A is the inverse element of A. In the set of integers, I have taken a number 5 plus minus 5 equal to minus plus addition with 5 equal to the additive identity 0. 5 and minus 5 belongs to the set of integers, and minus 5 is the additive inverse of 5, or otherwise 5 is the additive inverse of minus 5, reversely. Then now multiplicative inverse. These are the examples for additive inverses. Now multiplicative inverse. Multiplicative inverse. If A is any element in the set S and its multiplicative inverse is 1 by A, such that A into 1 by A equal to 1 by A into A equal to multiplicative inverse 1. So 1 by A is the inverse element of A, or A is the inverse element of 1 by A, whatever it may be. Operation is binary operations multiplication. For example, suppose 4 by 5 is a fraction belongs to the set of rational numbers Q. Then 1 is the multiplicative identity in Q, such that 4 by 5 into 1 equal to 1 into 4 by 5 equal to 4 by 5. 1 is the multiplicative identity in Q, and 4 by 5 means it implies 5 by 4. 1 by 4 by 5, that is 5 by 4 is the inverse element of the element, inverse of the element 4 by 5. That is 4 by 5 into 5 by 4 equal to 5 by 4 into 4 by 5 equal to 1. Multiplicative inverse, that is 4 by 5 is a fraction in Q, then 1 by 4 by 5. 1 by 4 by 5 is the inverse element of 4 by 5, that is equal to 5 by 4. This is the inverse element of 4 by 5. Like that multiplicative inverse is defined. So far I have defined additive identity. identity, additive inverse. Similarly, multiplicative identity 1 and its multiplicative inverse. In each and every algebraic structure, identity element is only 1 in the set. Whereas inverse elements are, for each and every element, there exists an inverse element for the corresponding element given in the set. See, now I am going to prove one theorem. In an algebraic structure, the identity element exists and it is unique. That is the theorem. Uniqueness of identity. Theorem 1. Uniqueness. Uniqueness of identity. In an algebraic structure, if the identity element exists, it must be unique. Theorem statement is, in an algebraic structure, if the identity element exists, it must be unique. That is only one. It must be unique means it is only one. In an algebraic structure, if the identity element exists, it must be unique. That is the uniqueness of identity. Yeah. That is proof. S star is an algebraic structure. It is an algebraic. S star is an algebraic structure. Suppose E1 and E2 are two identity elements belong to the set S. Suppose E1 and E2 are two identities in the set. Yes, we have to prove they are equal. There should be only one. E1 equal to E2. First, if E1 is identity, E2 is an element. If E1 is the identity element, E1 is the identity and E2 is any element, in S, we can say E1 is identity, therefore E2 star E1 equal to E1 star E2 equal to E2 because E1 is identity. This is expression 1. Similarly, if interchanging the nature of E2 and E1, now E2 is identity, E1 is any element. Now, see, interchanging the nature of E1 and E2 now, that is, now E1 is any element, E2 is identity. Now E2 is the identity and E1 is any element, then E1 star E2 equal to E2 star E1 equal to E1 because E2 is identity here. This is equation 2. Comparing the equations 1 and 2, left hand sides are equal. E1 star E2 star E1, E2 star E1 equal to E1, here E2 star E1 equal to E2. From 1 and 2, comparing 1 and 2, This is 1 or equation, this is 2. Comparing 1 and 2. E1 equal to E2. Therefore, the identity element is unique in any set. The identity element is unique because using this equation 1 and equation 2, in these two, comparing 1 and 2, E1 star E2 is E2, E1 star E2 is E1. Therefore, left hand side is equal, therefore right hand side is E1 equal to E2. Hence the theorem. Second theorem, uniqueness of inverse element. Now, theorem 2, uniqueness of inverse. Uniqueness of inverse. So, in algebraic structure, if the inverse element exists for an element, it must be unique. If the inverse exists in an algebraic structure, if the inverse exists, it must be unique. In an algebraic structure, if the inverse of an element exists, it must be unique. It must be unique. This is the theorem. Proof. S star is an algebraic structure. X star is an algebraic structure. X star is an algebraic structure in which A belongs to an element in the set S. Suppose A1 and A2 are two inverses of the element A. Suppose A1 and A2 are two inverse elements of A. If A1 is the inverse, if A1 is the inverse of A, if A1 is the inverse of A, we have A star A1 equal to A1 star A equal to E. If A1 is the inverse of A, the element and its inverse operating upon an operation gives you the identity. Similarly, if A2 is the inverse of A, if A2 is the inverse of A, then A star A2 equal to A2, A star A2 equal to A2 star A equal to E, which here A2 is the inverse element of E. Now we have to prove that the two inverses of A1 and A2, two inverses A1 and A2 are one and the same. They are the only one inverse we have the element of A. For that, I am plotting that if A1 equal to A1 star E. I can write it as A1 by A1 star E. I am replacing this A1 as it is star with E by A star E2. This one. A star A2. This E can be replaced by this A star A2. A1 is A1 star E because A1 star E is A1 and this E can be replaced by A star A2. By associative property, I associate this A1 star A together and star A2 I keep as it is. By associative property, A1 star A2. But A1 star A is E, therefore this is E star A2. You know E star A2 because E is identity, E star A2 is A2. Therefore you see A1 equal to A2. We got A1 equal to A2. This implies A1 is equal to A2. Therefore, the inverse element of A is unique. Hence the theorem. A1 equal to A2, therefore, the inverse of A is unique. We completed the theorem and we will stop here and we will continue the topic in the next video. Thank you.